Okay, so end of week 1, office hours, doing some 129 questions. Let's go ahead and get started. We'll start with number 8, and I'm going to need some help. What the heck is number 8?
Sure, I can show you the problem.
Yeah, let's take a look. So number 8 says, you keep adding lead chloride into water until no more will dissolve. What is the concentration of lead chloride in the solution? Phrased a little bit strange. It wants the concentration of lead chloride that will dissolve into solution. So this is actually a strangely worded solubility problem, right? So it's just PbCl2 solid goes to Pb2 plus 2Cl minus, both aqueous. Now, the phrases that are the key things to help us out are no more will dissolve. So if no more is dissolving, what point is that?
Oh, we reached the
saturation point.
Saturation point. Other word for it?
equilibrium.
It's the equilibrium. So that gives us a hint that we're going to be doing our whole initial change equilibrium. I'm doing this in water. The problem is doing it in water, so we start with zeros there, plus x for the lead, plus 2x for the chloride. We get x, we get 2x. I'm going to have KSP is equal to the lead concentration times the chloride concentration squared, which when I plug in my numbers, what's the KSP value for lead chloride from the equation sheet?
1.7 times 10 to the negative 5.
So that's going to be 1.7 times 10 minus 5 is equal to x times 2x quantity squared. Hey, how's it going? Come on in, grab a chair. Which we could just say is 4x cubed. Solve for x.
Can I grab a chair from another?
Yeah, or you could take this one.
Yeah.
That's fine too, yeah. I can't solve that in my head. 1.7 divided by 4 is going to be like 0.4 cubed root of 0.4. No, you do it.
4.25 times 10 to the negative 6.
No.
0.16.
Wait, I'm on the
0.016.
0.016.
Oh, yeah, 0.016.
1.6 times 10 to the minus 2 molarity. That's it. So, now, the part that becomes strange, and I'm not totally happy with the way this question is phrased, is asking the amount of lead chloride that would dissolve into solution. So that's the concentration of lead chloride that would dissolve into solution. And it's weird to talk about so this is the part where I always feel weird talking about like the solubility of a solid, particularly the molar solubility of a solid, because the solid is not in the solution. So molar solubility is the process of a solid going into solution. So when we talk about this molar solubility of the solid, that is the number of ions the solid will put into solution, or through the mole ratio, that's the number of moles of solid that will dissolve into solution. It's not the solid in solution, it's not like a solid floating in the liquid, it's moles disassociating into the liquid. So that's the amount that's not going to be solid anymore. And that should be it. So that's number 8. Questions? Let's go ahead, let's look at number 11. Do me a favor, just go ahead and read it real quick.
What minimum concentration of OH must be attained by adding NaOH to decrease the concentration of magnesium in a solution of magnesium nitrate to less than 1.1 times 10 to the minus 8 molarity?
Now you might have a different number here, because that number is randomized. So what's this asking for? So we're going to put in some amount of sodium hydroxide, and we want to get our magnesium 2 plus concentration down. So we have to think, okay, well, how is magnesium and hydroxide going to interact with each other? Any ideas? Let's look at the equation sheet. Is there a number for magnesium hydroxide anyplace? What number is given to us?
6.3 times 10 to the negative 10.
That's the KSP value.
Oh, like his.
6.3 times 10 to the minus 10. So what that suggests to us, right? Because one of the things we have to start working on this quarter is how reading a problem or just seeing chemical compounds gives us an idea of what chemical reaction is happening or what we should be thinking about. And so the equation sheet, those KSP values, those Ka values, those Kb values, they're giving us hints towards what's going to happen chemically. So when we see a low KSP value like this, we say, oh, you know what's going to happen? Magnesium hydroxide is going to form a solid. That solid is going to dissociate into magnesium 2 plus and OH minus. I know that's going to happen because I'm given a KSP value. That's what the KSP value means. So now I want to set up a solution where when I do this, I'm going to rewrite this someplace where I don't run into the edge of the board. So now when I set this up, I'm going to have magnesium hydroxide. I'm going to add the hydroxide in. The hydroxide should do a chemical reaction with the magnesium nitrate to form solid. After the solid is formed, I could say, okay, well, if I put in the exact molar equivalent amount, all my hydroxide runs out, all my magnesium runs out, I form all solid. That solid is then going to dissolve into magnesium 2 plus 2 OH minus. And I can tell how much this is going to happen from this value. But I want it to happen a particular amount. I want it to be such that when this thing dissolves, this is 1.1 times 10 to the minus 8 molarity. I want my solution to end up with that concentration. How much hydroxide do I need to make that work? Well, that's going to be an unknown amount. I have an unknown amount of hydroxide here. I'm going to have a plus 2x here, but I'm going to go ahead and use the x's. Now, this is a weird time to use the x's small approximation because I actually don't know what my question mark is, but I'm going to go ahead and just use it and say this is going to end up being approximately equal to question mark. I want to find the correct amount of hydroxide to make it so when I hit equilibrium, that's the concentration I have. Then I can just go ahead and set this up where I've got the 6.3 times 10 to the minus 10 is equal to 1.1 times 10 to the minus 8 times question mark squared. Can you solve for question mark? Notice the math is not hard, right? The math is like divide and take the square root. The setup, how we think about the problem, that's the tricky part here. Identifying what's happening chemically, and then identifying how we can frame that into a solvable problem. That's what we really have to work on this quarter. If I just give you equations like this all day and ask you to solve them, no problem. Question?
Can I ask why you're using the KSP for MgOH2? Like, how did you come to knowing that you had to use that?
The problem said we've got some magnesium nitrate in solution, and we're adding hydroxide to reduce the magnesium concentration to a particular level. So I knew there had to be some reaction happening between magnesium and hydroxide. And, I knew what reaction was going to happen. But if you didn't know, what you would do is you'd look at the equations sheet, and you say, well, what information do I have about magnesium hydroxide? And there's a KSP value there. So it turns out the reaction that's happening as you add the hydroxide is a precipitation reaction. Right? So that's the first thing. Oh, we're doing a precipitation. Now, KSP is about solubility. So we imagine I do the precipitation reaction as much as possible. I keep adding hydroxide until I knock out as much magnesium as possible. But that zero can never stay zero, so I know the minimum amount of, I know the maximum amount of magnesium ions I want left in solution, and I want to find the minimum amount of hydroxide to make that happen. Can I dump in extra hydroxide and keep the reaction going? Yeah, if I keep dumping in hydroxide, I can keep making the reaction happen. But I don't want the maximum amount of hydroxide, I want the minimum amount of hydroxide. So I'm looking for that equilibrium point. So I go ahead and I say, okay, I'm going to set up an equilibrium table where I have approximately 0 magnesium, because I've precipitated all of it out, and I've added some amount of hydroxide. I don't know how much. The equilibrium, so the solid that's formed, now goes through the equilibrium process of dissolving a little bit to get that 0 to be non-zero. And the problem tells us specifically, I want to get this value at equilibrium. I want that number or something smaller than that number left in solution. So I actually know what my x value is. I could put the x in because I know x is going to be 1.1 times 10 to the minus 8. So I could do question mark plus 1.1 times 10 to the minus 8 and solve the quadratic. I'm going to go with x is small and see what value we get for question mark, because I think it's going to be pretty big. Question?
So, because you're taking out the magnesium, the nitrate's still left.
Yeah.
So you're really just worried about, so the 1.1 times 10 to the negative 8, like there's going to be extra nitrate ions left.
Does the nitrate matter in this equilibrium?
Well, no, but I was just curious, like when you say you're trying to get the magnesium nitrate to be less than 1.1, you're assuming there's also extra nitrate.
Yeah. There's bunches
in there,
of
but
nitrate.
it's only the ones that are
Yeah.
okay. And then also, I'm assuming just as a conceptual, like because the precipitate forms, that implies that it has a much bigger magnesium hydroxide has a much bigger KSP than magnesium nitrate, correct?
Wait, say that last part again. Magnesium hydroxide
It has a bigger KSP.
much smaller
Or
KSP.
Smaller KSP.
Because KSP is always written in terms of the solid falling apart.
Yeah.
So a small KSP means stays solid.
Right, okay.
Right?
Yes,
Stays
that's
as
what I meant.
reactants.
It's
Yeah.
much smaller.
Much smaller.
Okay.
That's why I was about to say yes, and I was like, hold on, I think we got this backwards.
Yeah, okay.
Much smaller.
Smaller KSP.
Yeah. So the other thing that we're not worrying about, there's sodium ions floating around inside of here.
Okay.
Sodium hydroxide that we're putting in has a KSP value associated with it. The sodium hydroxide KSP value is enormous, is a really big value, because so it disassociates kind of completely,
Okay.
at least in the context of this problem.
Okay.
And that's how we set it up. That was number 11. I believe number 12, is number 12 similar, or?
It's what is the molar solubility of copper hydroxide in a solution buffered at pH 10, and it will have a hydroxide concentration of 1 times 10 to the negative 4.
So the pH part doesn't matter as much, right?
Okay.
pH can lead, so we're going to learn later on that pH leads us to talking about hydroxide concentration.
Okay.
So pH tells us about hydroxide concentration. Here's what I want you to try and do. That's number 12.
Yes.
Do me a favor, everyone, try number 12. What question did you have? What's your name? Brian, okay. Did you, were these questions ones that you want to talk about? 124. Yeah, I'm going to talk to you in just a second. So, everyone working on 129 stuff, try number 12, and then I'll come see how y'all did. I'm going to answer some 124 questions real quick and pause the video while I'm doing that. Yeah, you're great. Am I recording?
Like questions on like quizzes or tests, are they based off the graded questions or all of them?
All of them.
Okay.
With randomized numbers and randomized values. So let's go ahead and do number 12 together, then we can look at, wait, do we want to do, is number 13 a graded one?
No.
Okay.
I think we're struggling on 13.
Is 12 okay then?
Yeah.
Okay, let's do number 13 then. Okay, what is number 13? Read it to me.
Oh, okay. Hard water contains alkaline earth cations such as calcium, which react with carbonate to form insoluble deposits. When precipitate of calcium carbonate form if a 250 milliliter.
Ooh, keep going.
250 milliliter sample of hard water containing a calcium concentration of 1.7 times 10 to the power of negative 3 m is treated with the following. And then the following. A is 0.10 milliliters of 2.5 times 10 to the power of negative 3 m sodium carbonate, and then B is 0.026 milligrams of solid sodium carbonate. And then the answer's like yes, no.
Okay, so I made a funny sound when you read a particular word. Does anyone remember what particular word you read that made me go, oh? There was a particular phrase, and remember, one of the reasons I stress vocabulary in this class, and I stress like how we read the problems, the math always ends up not being that bad, right? The math almost always ends up being like division, multiplication, addition, subtraction, a couple logarithms later on, but the math is never that bad. The thing that everyone struggles with in this class is how the words of the problem lead us to thinking about something. And there was a particular phrase that made me like, oh, this is different than what we've been working on.
Is it insoluble deposits?
No. So what's the root of the question? What's the first part of the actual question, Sweat?
Will it precipitate?
Precipitate.
Does it say will it, or what's the...
Yeah.
Will
Will
it
it?
precipitate of calcium carbonate form? If and then.
So this isn't asking how much does it happen. This is just asking, will it happen or not?
Out.
Do you remember the problem structure from 128 that we use for will it happen or not? So this is different than a lot of the other problems. We've been able to skip the thinking we need to do here because I've always given you problems where you've got zeros. Here we don't have one thing being 0.
Are we doing some sort of like limiting reactant or something like that?
Almost.
Periodic yield?
Almost.
Percent yield?
129 things, you're saying, sorry, 128 things, you're saying 127 things. How did we figure out if something would happen or
Oh,
not?
like a G, like a delta G, or like a Q.
Yeah, there we go. Right, so it's the delta G, then the delta G leads us to KSP versus Q. Right, and we say, since we're trying to form a solid, we're going to ask ourselves, is the KSP bigger than the Q, smaller than Q, equal to the Q? If the KSP is equal to the Q, your maximum ions in solution, you're at equilibrium. If the KSP is larger than the Q, you need to move towards more ions in solution. No solid would form. If the KSP is smaller than the Q, ions need to come out of solution and form solid, so precipitate would form. So fundamentally, all this is asking us to do is solve for Q in each case and compare. Where we've got our 3 main cases. I'm going to go ahead and write down the 3 main cases. We could have KSP,
No, you're fine.
we could have KSP equal to Q. That would be at equilibrium. We could have KSP greater than Q. That would mean more products. We could have KSP less than Q, which would mean more reactants. The way that I always remember it is if I set it up so KSP is first, my greater than and my less than make little pretend arrows in my head that point the direction it goes. So I don't have to do my whole logic of like, products, reactants, products, how much do I have, how much do I need, right? That's my nice little trick. So what this means, let's go ahead and do A together. Right? Is it okay if I erase this part in green and we start doing it together? Well, first, let me check. Well, we'll do A together. Does this give you all like a little bit of a start to how you think about it? Again, the thing that made me be like, oh, this is different was the fact that it said, will it happen? Like, will it happen is not a how much will it happen, not what's the concentration, not what's the equilibrium value, which is where we do a full equilibrium table, just does anything happen? That's where we actually start every one of our processes. Now, the reason we don't do this in class very often is because every situation I set up is usually Q equals 0. And so we always know K is bigger than Q because K is always bigger than 0. So I'm almost always setting up a situation where we always know, oh, it's going to go towards product sum. Not always, because here's an example. So let's go ahead and do A together. I've got 250 milliliters of 1.7 times 10 to the minus 3 molarity calcium 2 plus.
Really quickly, that 1.7 times 10 to the negative third is her number, but that was the concentration of
Calcium ions.
calcium carbonate. But is that the same?
Calcium carbonate or?
So mine says that I have a calcium
Concentration.
Oh, I read that wrong.
Yeah, no worries. And then we're going to add 10 milliliters of 2.5 times 10 to the minus 3 molarity carbonate. Now, you don't just throw those two concentrations into your Q value because you need to do, starts with a D. Almost. Ends with ilution.
That's like the MV.
Yeah, you need to do dilution calculation.
That's it.
Right? So our total volume, when we add this together, we're going to have 260 milliliters total. So I'm going to do 250 times 1.7 times 10 to the minus 3 divided by 260. That's going to be equal to my calcium concentration. And then I'm going to do the same thing, except for it's going to be 10 times 2.5 times 10 to the minus 3. And I'm going to call this initial. Because this isn't an equilibrium value, right? We're pouring this together and seeing what happens. Then we're going to have that divided by 260. That's going to be equal to my carbonate concentration initial. And then my Q value is going to be my calcium concentration at the initial times my carbonate concentration at the initial.
I have a question.
Yeah.
Where it says 10 milliliters, for me it was 0.10
Yeah,
milliliters. I
same.
know.
Oh, 0.10.
I'm really struggling to follow along with the different numbers, just trying to compare it back and forth, but on ours, at least
Oh, that is 0.10.
Sorry.
Maybe I said it wrong.
So then
It's
it would
0.1
be-
milliliters for everyone.
Okay. So then it would be 250.1.
Oh, yeah. This would be,
So we're taking the
wow.
So we're taking the initial, the 250, and multiplying it by the molarity on the numerator, divided by the
Total volume on the denominator. Now, it turns out this one, now that it's 250.1 instead of 10, this calculation is kind of pointless.
Yeah.
Because the concentration is going to be approximately 250 divided by 250.1 is approximately 250. This one is going to be approximately 1.7 times 10 to the minus 3 still. Our calcium concentration isn't really going to change. Our carbonate concentration is going to be way dramatically different. It's going to be really small.
And that 1.7, that's the concentration of.
Calcium ion. So calcium ion concentration is approximately equal to.
So mine's 4.8.
Yeah. And the important thing here is, regardless of what your numbers are, is following the conceptual idea of what's going on.
Yeah, I'm trying to I'm trying to read the word problem and see how it's set up, and then when I look at your work, I'm getting twisted up because my numbers aren't even close.
Right.
So I'm like, wait, which number's which?
And this will happen every week because all of you have randomized numbers for your own calculations, except for a couple weird problems where if I randomize the numbers too much, the problem goes really bad.
Yeah.
So now we can go ahead and calculate the carbonate concentration, calculate our Q, and now you can do Q versus KSP and figure out will it happen or not by doing Q versus KSP.
And then you would do the same. So for the next one, I have a weight.
Uh-huh.
So you'd go from weight to milliliters. Or
You go from weight to
molarity.
moles to
Moles.
molarity.
Okay, because that one, okay, you don't even, okay.
So let's go ahead and do this calculation and figure out will anything happen real quick. So I'm going to do 0.1 times 2.5 times 10 to the minus 3 divided by 250.1. And I'm going to get 9.99 times 10 to the minus 7. Then I'm going to go ahead and calculate my Q value. That's going to be times 1.7 times 10 to the minus 3. And I'm going to get 1.699 times 10 to the minus 9.
Can
right?
Can I ask you a
Really
question?
small number.
Is this supposed to say sodium carbonate, or is that
Yeah.
supposed to say calcium carbonate?
Sodium carbonate.
Okay, and the only reason that doesn't matter is because we're looking at the carbonates.
Yes.
Okay.
Right. Sodium is a spectator ion.
Okay.
What is our K value for calcium carbonate? Somebody help me out. Y'all should have equation sheets out. 3.3 times 10 to the minus 9. So, you notice 3.3 times 10 to the minus 9. In this situation, my 1.699 times 10 to the minus 9, my KSP is larger than my Q value, because it's 3.3 times 10 to the minus 9 versus 1.6 times 10 to the minus 9. They're almost the same, but for these numbers, and since everyone has different randomized numbers, your numbers might flip this. Right? This is for this particular problem. So you have to do it for your particular values and see, is my KSP, is my Q bigger or less than my KSP for your particular values?
And this is Q. We just figured out Q.
Q is this, yeah.
Oh, wait, sorry.
Q is the concentration of calcium ions initially times the concentration of carbonate ions initially.
And because,
So we had to do our dilution calculations to get our initial concentrations so we could calculate Q.
okay. And the first concentration, because the initial and the final volumes were so similar, we just, okay.
Yeah, I didn't even bother doing the math.
Okay.
I could, but I didn't bother. Question?
I'm a little lost after the M1V1 equals M2V2. What do we use that equation for?
So we have to find, so because we're mixing two solutions together, we have to find the new concentration of each component. So we use that M1V1 equals M2V2 twice. Once for the calcium concentration, once for the carbonate concentration. And those are the initial concentrations, not the equilibrium concentrations, because we don't even know if a reaction is going to happen or not yet. So we look at our initial concentrations and we calculate a Q value from our initial concentrations. And we compare that Q value, our what we call a reaction quotient, that's why we use the letter Q for it. We compare that Q value to our KSP value to see if we are bigger than equilibrium, smaller than equilibrium, or equal to equilibrium.
And in this case, the KSP we're looking for is calcium carbonate.
Yes.
Okay.
Because the calcium and the carbonate are the two things that are going to react. Sodium, super soluble. I don't think it even tells us where the calcium comes from. Probably calcium nitrate. Just calcium's in water from a lot of different sources.
So if the Q is greater than the KSP, then more products are needed and the reaction's going to the right.
We'll say that again. If the Q is greater than the KSP.
If Q, because my Q is greater than the KSP, so it means the equation's going toward the product side.
Opposite. Remember, so here's the way I always think about Q versus KSP. I always just think about the numerator. The numerator is products.
Mm-hmm.
If Q is bigger than KSP, that means you have too many products compared to your equilibrium.
Okay.
So you have to get rid of products to get back to equilibrium. If your Q is less than your KSP, you don't have enough products. You have to make more products in order to get to equilibrium.
So for the will it happen, does that mean like the precipitate forming?
Yeah, so the problem specifically asks, will a solid form?
And then if it's not at equilibrium, it doesn't?
Well, since this is a KSP reaction, let me write this up here real quick. Since we're looking at a KSP reaction, the reaction we are considering, what does a KSP reaction always tell us? KSP is a particular reaction we write down. Solid dissolving. So we've got calcium carbonate, solid, dissolving to calcium 2 plus ions, plus carbonate ions. So if I need to be forming, I need to push this towards reactants if solid is forming. So that means I need my KSP to be smaller than my Q if a solid forms. So there's a lot of conceptual ideas. The math for this is not very difficult. The conceptual work is really heavy. And a lot of this conceptual work is 128 review. I'm going to let you all work on B. Try your individual numbers. See if you can figure out what's going on. So you all convinced me that I should do number 14, even though it's a graded question. What is the question?
Find the equilibrium concentrations of the cations and anions in solution when you dissolve as much as possible calcium fluoride in water. Use, and that's it.
You can all do this. You can all do this. This was like yeah, we did this one together already.
We're just trying to make sure we're doing it right.
Okay, so somebody tell me what to write down.
Mine says BAF2.
You have different randomized compounds.
So we're writing BAF2, 2 arrows to barium plus
Okay, let's go ahead and since 2 of you have barium.
2 fluoride. I didn't mean to do that. I'm sorry.
Okay.
I was just reading one. To 2 fluoride minus.
Yep.
Okay.
This is in water, so what's our initial amount? It's asking for equilibrium, so that gives us the hint that we're doing an equilibrium table. Do I include the solid in the equilibrium table?
No.
Nope.
0 for the initial.
0's for the initials because we're doing the solubility in water. How much is my pluses?
Plus x and plus 2x.
Does it matter whether it's barium or calcium?
No.
No, it comes out the same. Your KSP values are different, so watch out for that. And then I'm going to have x, I'm going to have 2x, I'm going to have KSP.
And the KSP is 1.5 times 10 to the negative
For
6.
barium fluoride or?
Yeah,
Okay.
barium fluoride, 1.5 times 10 to the negative 6.
So what's your question?
And then from there, we are just finding x, right?
And then don't you plug it in after that? Find the
Yeah.
cation and the anion?
Yeah.
Okay.
Okay.
Yeah, that's it.
Okay.
So for anion, it's just 2 times the x that we find.
Yeah.
Like there's no squared.
Nope. The squared is when we're doing the equilibrium calculation to find x, not when we're getting the concentration at equilibrium.
Okay, so do we use the molar solubility we get? It's like barium, right? So do we use that molar solubility to find the anion? Or do we use the
Yeah.
KSP? Okay.
Well, you're using the KSP to find the molar solubility, which is going to give you the x value, right? So this value here is concentration of anions at equilibrium, right? And that value is just 2x.
Yeah.
So if we find our x value, 2x will be our fluoride concentration, or whatever your randomized anion is. Yeah, you all know how to do this one. You're doing great.
I was still having trouble on number 13 because I converted the
13b?
Yeah, 13b.
Okay.
So I converted the milligrams to moles.
Uh-huh.
I don't really know what to do after.
Did you divide the moles by total volume to get molarity?
Yeah.
Oh, yeah, same.
So would I just plug that into the same like M1V1?
No, because that's already your concentration of carbonate. So that is your carbonate concentration initial. You just plug that into your Q expression.
Oh, so that's the Q?
That is part of the Q. I wish we talked about this again before I erased it all.
The other part of the Q is the original concentration of calcium.
Oh, where you multiplied it?
Yeah.
Oh, okay.
Is that, you got it?
Yeah.
Okay.
So pretty much what we're learning from that problem is that if K is greater than Q, then it's going to be no, it won't like form.
If K is greater than Q, ions will be in solution. You will not form solid.
Okay. If it's the other way around, you will form solid.
Ions will form into a solid in solution. Yep. And most importantly, so that's the thing we're learning, but the whole process of, can I compare Qs? Can I make sense of initial conditions to figure out whether a reaction is going to happen or not is the real thing that you want to be learning from this. Not just like the math part of it. It's the conceptual part that's more important.
Yeah.
Can you do a quick glance on what I wrote here and make sure I didn't make some silly mistake? Because I'm going to reference that quite a bit.
Okay. KSP equals Q. KSP greater than Q, more products needed. Does not precipitate, ions will be in solution. KSP equals more reactants needed, does precipitate. Yes,
Okay.
that is generally true
Okay, thank you.
for KSP reactions. Okay, I'm going to pause this.